So since we understand the oxide degradation model, and next we will need to understand the oxide breakdown model. And the well-known oxide breakdown model is called the percolation model. And this percolation model can be successfully explain the thickness dependency, critical trap density, and also the area dependency. And also percolation model can help us to understand the salt breakdown, the progressive breakdown, and hard breakdown. So first, just let me explain the percolation model. So electron traps are randomly generated in the oxide. And we can characterize the trap by consider as a sphere. And when the breakdown happens, that means we start to have a conducting path formation between the one side to the other. So once during the stress, you will start to generate this defect here. But when the defect is aligning with one conducting path here, then the breakdown occurs here. And the critical trap density is equal to the total number of the trap over the test volume necessary to form a conducting path. So by using the percolation model, we can successfully to model the wave distribution very well. So you can see this is one of the data to show that the experimental result and simulation are fitted very well. On the other hand, the decrease of the wave slope for the zinc oxide is an intrinsic static property of the degradation mechanism. And this can be also successfully simulated by considering the percolation model. So you can see this is wave slope beta versus oxide thickness. With a thinner dielectric, the beta always decrease, and that also can be justified using the percolation model. And the critical electron trap density is reduced when oxide thickness is scaling, which is also can be explained by the percolation model. And in these two papers, they show that when we scaling down our oxide thickness to a certain level, probably there's only one trap is needed to form the conducting path. So for example, you can see in the case below 4 nanometer, this one is almost means that there's only one trap is needed. And also on the other hand, this also showing that once our oxide is scaling to a certain level, this reaches saturation. So that means we only probably need one trap is enough to form the percolation model. And this is an area dependency. So we can find out that the y-axis is a QBD and x-axis is an area. With a thick dielectric here around like 11 nanometer, so we can find out that the QBD is only like the factor of the 2 of the drop. But if we have the very thin dielectric here as a 4.3 nanometer, there's around like 3 to 4 order of magnitude drops. And therefore, the thick oxide, we have a large wave slope but small area dependency as shown here. But the thin oxide, we have a small wave slope but with a large area dependency. And next, we will continue to discuss the understanding of the soft, progressive, and hard breakdown. As previously we have been shown this graph, already mentioned that the breakdown is not instantaneous. So you can see the leakage current is increased slowly after the formation of first breakdown path. So once we found out that the noise is increased, that already suggests that the first breakdown path is already generated. And then the leakage current is increased slowly until the hard breakdown. So we can also see this schematic showing that once there's a small hump happen, that already suggests there's a soft breakdown happen. And then there's a certain time between the soft breakdown and hard breakdown. So that's what we call the progressive breakdown. In the end, the dielectric reach to the very high current. That's due to the hard breakdown. So here is the two possible process from the soft breakdown to the hard breakdown. For example, it can be only one breakdown spot. From the beginning, it's small, but this breakdown spot is continue growing, become larger and larger, and in the end, the circuit failure because the high currents go through this breakdown spot. Or it can be multiple breakdown spot. First, the breakdown spot happen here. Second, we have here. Third one, we have here. But then, afterwards, finally, there's a one that in the end have very high current go through and become the hard breakdown. So the time between the soft breakdown and hard breakdown, this is a very obvious time for the progressive breakdown. So soft breakdown make classical dictation of the breakdown problem, and therefore, for example, we have to introduce some alternative method, for example, based on the current noise increase. You can see if we only look at this typical current versus time, the small increase already suggests a certain degradation of the dielectric. And if we try to plot in the different scale, and then very obvious noise can be observed here, and therefore we should also consider to use current noise increase as a spec to identify the soft breakdown. And here is also one of the experimental results for the progressive breakdown. So you can find out that in the case of a progressive breakdown, here this is case for the minus 3.5 volt. So it takes around 100 seconds. And if the low bias, it takes around 300 seconds from the soft breakdown to the hard breakdown. And the last part, we will talk about the available model for the acceleration testing. In the end, we hope to have the acceleration model allowed to extrapolate lifetime, but the acceleration model will be changed depends on the different mechanism and different oxide thickness. In here, we summarize, as you can see here, in the case with a large 5 nanometer, there are the two different acceleration models very often used. One is E model, one is 1 over E model. These all based on the FN tunneling mechanisms. And in the case of the below 5 nanometer, the acceleration model is based on voltage, and which is due to the direct tunneling mechanism. And here's some of the experimental data to show that the E model or 1 over E model fitting. So you can see this is a TBD and versus different electric field. So the E model can fit the data very well. Or this is TBD, and then this data can be also fit well for the 1 over E model. And one of the things we need to be careful is about when we do the acceleration testing and do the fitting, we only fit in this region, which is a bias, which is larger than our operating bias. But once we use the E model or 1 over E model, it can be when we fit to the low field, either overestimated or underestimated here. So therefore, we have to make sure that the mechanism here should fit it with the model we use. For example, the E model is based on the thermochemical model, and 1 over E model is based on the anode hole injection model. So we have to understand the degradation to see that whether our degradation is aligned with the anode hole injection or aligned with the thermochemical model. And once we do have the dielectric scaling, we found out that the tunneling mechanism is changed. So in the case with a thicker dielectric, the FN tunneling is dominant. Then FN tunneling dominant means that electric field determines energy at the anode side. That's why we use the E model or 1/E model. But in the case with the thin dielectric, actually the gate voltage determines the energy at the cathode. And this voltage will determine the leakage current, and that's why we use a voltage exertion model in the case of the oxide below 5 nanometer. So here is one of the data from the literature showing that in the case, this is oxide thickness between 1.3 and 5 nanometer, and the power law model can be fitted very well. So if we try to compare the TDDB and lifetime in the case of the 2.8 nanometer versus the 10.8 nanometer. So this is 10.8, this is 2.8. And the drop in lifetime at the fixed gate voltage due to temperature, area, and percentile. So that means in here you can find out there's only one order magnitude decrease in the thick dielectric, but in the thin dielectric there is a order of magnitude decrease. So that's why the oxide reliability is a potential showstopper for the further downscaling.